Hello, we're back with another set of work done and energy questions. This time we're starting with an experiment. We haven't had one of these for a while, so that'd be good practice. We've got a student wanting to carry out an experiment to determine the input power of a small electric motor without using electrical meters. The motor is used to lift light loads. Efficiency of the motor is 15%. So how can we determine the input power of the motion? So we need to include the measurements taken, the instruments used, and how we can determine the input power of the motor. Right, so let's think of the things that are going on. If we've got, quick sort of snapshot of what's going on here, we've got some motor that's lifting up some mass here. So we're going to want to know things like, well, how far has it moved in meters? What mass has it got in kilograms? And then, well, how quickly is it moving up there? Because we wanted to determine power, so that is going to be work done per second. We've got joules per second is what we want to end up with. So we're going to need to have time, and we're going to need for joules to have a force times the distance. So these are all of the things that we're putting into here in order to get power. So if we were going to have all of this in a table, we'd want to set up the first columns would be the things that we're going to set ourselves, so mass and distance. They'll be the things that we can define before we start. Then the things that we're going to measure that we don't know, so we'll measure it during the experiment, so how long it will take to lift it, a particular mass through a particular height. And then we're going to want to have our calculations off of the back of this. So we want to have output power and then input power. So these are all the bits we've got. And now we can just say, well, what are we using to measure each one of these? So we can say we're going to measure mass of load using scales, using set of scales. So that's the first thing. Measure distance lifted using a meter rule. Distance lifted using meter rule. So these are all like bullet point things that you can just write out as separate sentences. Then we can say, raise the load using motor and measure time taken. Measure time taken using the stopwatch. So that's dealt with all of our measurements here. And now we've got our calculations. So we can say calculate output power, and that is going to be equal to the force times the distance over the time. So that is the mass multiplied by g multiplied by the distance divided by the time. That is our output power. And then we can say calculate the input power, which is going to be equal to the output power divided by 0.15, the 15% efficiency. So it's a very formulaic approach here. You can think of these, as I say, as being bullet points. You've got 5 things here. Once you've got your table sorted, then for each column in the table, you can say, well, what is it and how are you going to measure it? What equipment are you using? So for each bit, you've got what the variable is, or what measure we're taking, what equipment you're using to measure it or such like. And then for the later bits, we've got, well, what are the calculations, what formula are we using in order to work these things out. And then of course you've always got at the end that you can say you can average the input powers to get a final answer. So depending on how many marks they actually wanted, you could then decide how much of this you're going to want to put in. But potentially here we've got maybe 11 things that we've said. Each column has got what the quantity is and how we're either going to measure it or calculate it. And then we've got an averaging thing at the end. So that's 11 statements that you've made all in that. So that should be enough to pick up 4, 5, 6, 7 marks, whatever they've decided to put into the question. Right, next up, define a vector quantity. So a vector quantity is a quantity that has both magnitude and direction. Give one example. So velocity, say, we've got loads of them: force, acceleration, momentum, they're all over the place. Figure 3.1 shows a force F at an angle 30 degrees to the horizontal direction. The horizontal component of the force F is 7 newtons. Calculate the magnitude of force F. So if we'd resolved that, the horizontal component is F cos of 30 degrees, and that is equal to 7. So F is going to be 7 divided by cos 30. Cos 30 is root 3 over 2. So that would be 14 root 3 over 3 newtons. The force F moves an object in the horizontal direction. In a time of 4.2 seconds, the object moves 5 meters. Calculate the work done by the force. So the work done by a force is the magnitude of force multiplied by the direction moved in the in the direction of the force. Or we can just say, well, it's the component of the force that we're moving in that direction. It's the same thing. If we take the component of the direction that we've gone in the direction of the force, that will be a cos 30. Or if we take the component of the force in the direction that we've moved, that is a cos 30. So it doesn't matter which one we do. So we're just going to be doing 5 times 7, a force times a distance, which is 35 joules or Newton meters. The rate of work done by the force is going to be 35 divided by 4.2. So calculator, 35 divided by 4.2 is 8.3 recurring, so 8.3 watts, seeing as we're at 2 significant figures. So that's all good. Figure 3.2 shows the forces acting on a stage light, okay, of weight 120 newtons. That's in the picture. The angle between the two cables is 90 degrees. Yep, we've got 70 on one. State the magnitude and direction of the resultant of the two tensions of the two cables. Right, okay, the resultant of the tensions of the cables must be, this thing's in equilibrium, which it is, it's held stationary, must be the opposite of the weight. So it would be 120 newtons upwards. Sketch a labelled vector triangle for the forces acting on the stage light, hence determine the magnitude of the tension T. Okay, so we've got 120 going straight down, and that has got to be cancelled out by these two tensions here. So we can have one of them going up here and the other one coming up here. We know that's 90 degrees. That is 70, and that is T. So we've got the T squared plus 70 squared equals 120 squared. So T squared is going to be 144 with 2 zeros, minus 49 with 2 zeros. So we just need to figure all of that out. So we can take 5,000 off and add on 100. So that's going to be 9500. So T is the square root of 9500, which is 10 times the square root of 95. So it's getting, closer and closer at the end. 95 square root of 95 is equal to 9.74. So 97.467. We've only got two significant figures, but we'll say first of all 97.47, and then we can say that is 97 newtons to two significant figures. So yeah, quite a nice little question. Nothing particularly difficult, but sometimes we forget how to draw these vector triangles. They don't come up as often as some of our other approaches. We can get so used to just resolving things all the time that we can forget about these triangles. All right, now we've got power can be measured in watts. Define the watt. So what is 1 joule of energy transferred per second? Now, an electric motor driven crane is used to raise a load of bricks, mass 700 kilograms, through a vertical height of 8.5 meters in a time of 45 seconds. The efficiency is 30%. Calculate the gravitational potential energy gained by the bricks. I think that's probably an EP that they put there. The P's just disappeared. So EP is equal to M times G times H, which is 700 multiplied by G multiplied by 8.5. So 85 times 70 is that, and then multiplied by 9.81. 5.8 times 10 to the 4. 5.8 times 10 to the 4 joules. The output power of the motor driven crane, so P out is going to be 5.8 times 10 to the 4 divided by, how long did it take? 45 seconds divided by 45. So that's 1.3 times 10 to the 3 times 10 to the 3 watts. And then the input power, because that is just 30% of it, so divide by 0.3 gives us, so yeah, P out, let's just say what we're doing, divided by 0.3, which gives us 4.3 times 10 to the 3 watts. So some pretty straightforward power and efficiency calculations. Right, to wrap up, we got a car of mass m at rest. Constant net force F acts on the car, moves distance x in the direction of the force. The final velocity of the car is v. Write down the equation for the work done by the force. So that is going to be, well, the force times the distance moved in the direction of the force. So it's F times x. An equation relating force to acceleration A. So F equals ma, just putting down Newton's second law for constant mass. Hence show that the kinetic energy of the car is given by this. Right, so we've got a half mv squared, which is the thing we're familiar with. You'll notice it's got no x and no a, so we're going to need to scrape the x and a out of all of this. So x is equal to, so that's the distance travelled. That is going to be the average velocity multiplied by the time. The average velocity is going to be v over 2. So vt over 2, so we can use that for x. The acceleration is the change in the velocity divided by the time. So that is, so delta v over delta t, which is v over t. So if we put these things in, then we're going to be all right. So ek is going to be equal to the work done, which is equal to f times x, which is equal to m times a times x. And now we can put in what these things are, because we've got a is v over t. So we've got m times v over t multiplied by x, which is v times t over 2, which gives us, the t's are going to cancel, and we're going to get a half mv squared. There are probably other ways of doing that as well, but that seems fine to me. Usual thing of look what isn't in the formula and what you've got in the starting ones, and then work out how you can eliminate them. The braking distance of an empty van travelling at steady speed on a level road is 50 meters. Now the van is now fully loaded with goods and travels at the same speed on the same road. Explain whether or not the braking distance would be the same. Assume that the driver applies the same braking force. Okay, so more goods. Therefore mass is up. Therefore kinetic energy is up. This is the usual chain stuff that we do. Therefore greater work done required to stop truck. Greater work done required. As F braking, so the braking force is the same, therefore the distance of braking must increase. So it's just a chain all the way through. You've got more kinetic energy, so we have to apply the force for longer over a greater distance, because we got this bit here. You know, work done is force times distance. The work done has gone up and the force hasn't changed, so the distance must go up. So we're just going through that whole chain. You know, find the first thing that's changed, fully loaded with goods. That's the mass has gone up, the energy's gone up, need greater work done, force hasn't changed, so the distance has gone up. So nice, there we go. It wraps those ones up.